We're excited to be here to talk to you about MIT's energy initiative and some of the specifics within that. My name is Doug Spreng. I'm a MIT alumnus, class of 65. I'll be the host for our two speakers here today, who I'll introduce in a second. First, I'd like to express my appreciation to Kevin Chen, who unfortunately couldn't be with us today, but he helped set this up, and also Alice Ryan, who's helped us with the logistics. So thank you, Alice. So as we all know, the world's energy challenges are enormous in scope, and it would be hard enough just to meet the growth in energy requirements. But when you start talking about replacing petroleum fuel-based ways of, or coal-based ways of generating energy with renewable, and you consider the terawatt-scale that you're talking about and everything, you realize that to address this challenge, you need some major breakthroughs in the cost and the scalability of the renewable energy. And we're seeing some successes here and there along the way, but we're a long way from achieving that result. One of the neat things is, though, as trained engineers or scientists or people who have worked in technology industries, here at Google, for instance, and elsewhere in Silicon Valley, we know that technology can be a major leverage factor in terms of addressing issues like cost and scalability. And so that's one of the reasons for being optimistic about what we can do. So we're here this afternoon to explore with you all some of the possibilities of addressing this challenge, particularly in the area of solar. And we'll tell you a lot more about it once we get into it. We call this program MITEI on the Road. It's the MIT Energy Initiative. So MITEI, Energy Initiative, MITEI is how we pronounce it. The on the road basically means that we want to bring MIT to you and tell you more about the research that's going on at MIT in the area of energy. Because we know that many of you are extremely interested in this, and we want to tell our story. The Energy Initiative, and I need to advance the slide. Okay. Is this what I wanted to do? Yeah. The Energy Initiative at MIT was kicked off about 3 or 4 years ago by Susan Hockfield, who was at that time the new president. Since then, at this time, even over 20% of the faculty is actively engaged in energy research. There's a MIT Energy Club that was established about the same time. It currently has 1,700 members. It's a completely student-run organization. The consequence of looking at this is that energy has become a huge program at MIT and has evoked a really passionate response on the part of both students and faculty. Daniel Enderton, who's sitting down here, will be our first speaker. He's a former president of the MIT Energy Club. He's going to give you a brief overview of MITEI, followed by a more in-depth presentation on the Sustainable Energy Revolutions Program, or affectionately called SERP, S-E-R-P. So Daniel's going to tell us about that. First, a little history on why we're doing this MITEI on the road. In April this year, the MIT Alumni Association conducted a survey of its alumni and wanted to find out, they wanted to test basically the alumni's interest and ideas for further, more significant engagement in the area of energy and environment. And so we designed a survey for the alumni and sampled the base, and the results that we got were pretty amazing. And one of the things that was surprising about the results were that they were totally uniform. It didn't matter what kind of course you took, what generation you graduated in, or anything like that, whether you donated or not donated to the Institute. Everybody had the same kind of feeling about energy and the environment. And in fact, 70% of the alumni surveyed described their personal interest as either strong or passionate. And about 20-some% of them actually said passionate, which is a kind of an off-the-charts kind of a result, I think. I don't know how many of you have ever answered passionate to a survey. It's the first time I ever did, so I found this kind of amazing. And so we felt like we really had something, but and it gave us the reason for bringing MIT more out, basically on the road, if you will, to to the people that are out in the regions. Because the people in the regions said, hey, we don't have to go back to Cambridge, Massachusetts to find out what's going on. We'd like to know more about it where we live and work. And so that's one of the reasons why we're doing this here. Also in the survey, alumni indicated their areas of interest. And the biggest one was in the area of renewable energy, particularly solar was the strongest, wind was number 2, and also in storage as a key enabler for being able to store these more intermittent sources of energy to be used for later on. And so those were all really indicated as very, very important subjects to go over, and the technology research going on in those areas, what they want to know about. So that's why we've asked Professor Tonio Bonacisi to come here, talk specifically about solar. It seems to be one of the more interesting areas for just our MIT alums, but I think out here in California it's even more significant. Now, why would we bring MIT to Google? Now, yeah, we know there's quite a few MIT alumni here, but a lot more that are not. And 2 reasons, I think. Number 1 is your company is extremely well known as a very environmentally oriented and sensitive company, and we understand that that there's a lot of personal interest in the employees here as well. And the second thing is a large number of technical people and who can grasp the technical significance of the kind of work that we're doing. So those are the 2 major reasons for this. But we have to admit, it's kind of a test, to see how it goes, see what the reaction is, and so on. Now, of course, out here in California, the solar revolution is in full force. We got dozens of solar startups. We got billions of dollars of venture capital money that have gone into this. In the Bay Area alone, in the state of California, with its Million Rooftops program, is promoting solar on the roof and so on and so forth. So, we live in an environment out here where this is a really big issue, and we're blessed with having a wonderful climate, too, to help solar along. That's another reason why we asked Tonio Bonacisi to be our first speaker in what we hope to be actually a series of events. So thinking maybe about once every 3 months to have a new speaker in these topical areas that we mentioned. Okay, so Professor Bonacini is going to follow Daniel Enderton in the program. We'll talk about some of the technical challenges and some of the possibilities of how we can scale up to the terawatt level with solar photovoltaics. So here's the agenda. I just did your welcome. Daniel's going to give the overview of the energy initiative, and then followed by Tonio to the Terawatt-Scale photovoltaics. And then we'll have time for Q&A at the end, as long as you'd like, actually. So Daniel's going to be about 15, 20 minutes. Tonio's going to be about 30 or so, and then Q&A. So there we go. Daniel, take it over.
Thanks, Doug. So as Doug indicated, I work for the Energy Initiative. I'm the executive director of the Sustainable Energy Revolutions program, which is basically an extremely long-winded way of saying that my job is to help build renewable energy research programs. And so actually what I want to do real quick is just kind of give you a quick overview of some of the things that are going on in energy at MIT. I would be potentially a good sort of resource just to sort of help facilitate connections between yourselves as engineers and engineers back at MIT, if that's of interest. And I'll also just talk a little bit more about my program, something sort of close to my heart. Actually, I don't know if you can read this from back here, but we were fortunate to have the president come by a couple weeks ago, and he gave a talk on energy, but also did a quick whirlwind tour of some labs beforehand. And some students talked their professor, Vladimir Bilovich, into getting the president to sign a deposition chamber for him. And so it says, good work, Barack Obama. And so now they're trying to figure out how to sort of encapsulate that so that the rigors of lab use doesn't sort of wear it away over time. So as Doug said, the Energy Initiative's been around for 3 years. It was started by our president, who came in just before that, and this is actually one of her major initiatives. She's really working to sort of harness the enthusiasm and direct the Institute towards energy. And out of which has formed the MIT Energy Initiative. It has 4 main parts: research, education, campus energy, and outreach. Research sort of spans quite a gamut of research, and it's really driven by what the faculty's interests are. There's quite a bit, 85% of our primary energy comes from fossil sources, so a lot of it just thinks about how to produce and consume fossil energy more efficiently, both supply side and demand side. a lot of it, and probably the majority of the research that's going on, is sort of looking towards renewable energy and storage options, sort of transforming the energy systems of tomorrow. A lot of also just sort of basic undercutting science that sort of cross-cuts a lot of technologies, systems analysis, so on and so forth. Education, there's definitely a dearth of talent to be able to go into the energy workforce, develop technologies, implement new business plans and that sort of thing. And so there's a major effort underway to sort of educate, sort of develop curriculum and programs towards educating students to go off and work in the energy field. Campus energy, if we're going to get serious about doing work in energy, we should look at our own carbon footprint, our own energy use, and see what we can do about it. And we have a rather old campus that affords us many opportunities to think about how one retrofits existing building stock. And then finally, outreach. There's definitely there's an elevated level of public discourse on energy at the national scene. A university can have a really good role in terms of trying to be an honest broker about sort of the intersection of technology, policy, economics, regulation, and try and sort of help to sort of guide policy and decision-making and so forth. And so there's been a lot of outreach work really focused at a kind of a national level, which I'll highlight. And so what I'll do is I'll just kind of give a quick example of something that's going on in each one of these areas. The one that I'll do the least is research, simply because Tonio is going to give you some really directed comments and research. So all I just want to do here is say that solar energy is our most sort of robust program right now. There's over 40 faculty that are working in this area. The only thing that I kind of want to get across with this slide is just simply that we're trying to sort of work with all sorts of different key players. We think it's really important working with industry, both big, like any, but also small, a lot of startups, building philanthropically supported programs, building government-supported programs, working with other nonprofits like Fraunhofer and Masdar. They all have really important roles to play, and we think it's really important to sort of be able to team with all of them. Education. So at a lot of universities, you take a very deep dive into your program, chemical engineering, EE, whatever it is that you're doing. But if you want to go on and work in energy, oftentimes a lot of context is needed. So for example, let's say a student from Tonio's lab is sort of studying some defect engineering, but they're interested in maybe commercializing something that they're developing. Well, they really need to know some things about business. They need to know some things about sort of economics, policy, basic science, engineering, so on and so forth. And so the idea is that undergraduates now have the opportunity to take this minor, which is the first kind of cross-cutting institute minor that we actually have at MIT, with the idea is that they complement their sort of core course of study with other areas like energy science, social science, and sort of technology and engineering. The idea to sort of prepare a more well-rounded student when they want to then exit the institute and go off into the workforce. And actually, a really important part of that as well is that it includes sort of research and very hands-on projects even at the undergraduate level. Campus energy. So we have a lot of really old buildings that don't have sort of the latest sensors and so forth. And so here's a really good example of actually a student project aimed at reducing electricity consumption for lighting purposes. The building on the upper panel is the Frank Gehry's Data Center. It's the Electrical Engineering and Computer Science building. And all around it are these older buildings. And so they've set up cameras in the windows. And this is the lower left panel is the camera looking at one of these buildings. And there's an algorithm such that it takes a picture every 20 minutes. It's figured out sort of which lights are on and which are off, and then sends an automated email to the occupants of that room if they've left their lights on, to sort of give them sort of a nudge, sort of a behavioral prompt, so to say, which is kind of a nice workaround when you have an old building stock. Something really similar, chemistry fume hoods. If you leave like a modest-sized fume hood open, it's about the same power consumption as a house, and so. And it's very easy to leave these up when you're done with your experiments or when you're in the middle of it. And so similar sort of thing, putting in sensors to automatically sort of prompt the users to close the fume hoods when they're done. And the Department of Chemistry expects to save $100,000 annually just from implementing these sensors in the fume hoods. So these are a couple of things that we're trying to do on campus. actually, something that may be of interest to you guys is there's a lot of interesting research that's going on too in terms of things like trying to do remote sensing to detect opportunities for energy efficiency improvement. So some thermal imaging, sort of a spectrum from satellite or land-based systems. Actually, it's Professor Sanjay Sarma, someone who works with Tonio Bonacisi. So if anyone's interested in going into that in more detail, I'm happy to chat about it afterwards. And then finally, I'll just mention a little bit about outreach. So like I said, we've tried to take on these series of studies that are really focused on doing sort of honest assessments of different parts of the energy sector. Here's a few of our studies that we've done on the left, done one on coal, nuclear power, a DOE commissioned one on geothermal, another one on sort of looking forward in the light-duty vehicle transportation fleet in the U.S. Actually, the three on the kind of upper left have actually all resulted directly in legislation at the national level. For coal, in the case of policies to encourage demonstration scale facilities for carbon sequestration, because that's kind of one of the impedances to understanding if that is going to be a viable technology to deploy at scale. The geothermal report was kind of one of a number of pieces that sort of helped prompt the DOE to resurrect their geothermals program, which had previously been zeroed out. The three that we have ongoing right now are solar energy, natural gas, and the future of the electric grid. You can actually bother Tony about it afterwards. He's one of the authors on the solar study. For natural gas, it's about halfway through the study, and they're coming up with some really interesting results. They've done a really in-depth sort of supply assessment of shale gas, and they've really helped to show just the absolute abundance of shale gas that we have in this country. I mean, sort of available at the $5 to $7 an MMBTU level now, but that price is going down, and so that really changes sort of the energy dynamic in the U.S. And so these are all available online. You can read the reports, you can see the studies. I can give you the links to them. They might be of interest. And so with that, what I'll do is I'll just describe a little bit about the program that I'm working on. And so there's kind of two pieces to it. The first is the Solar Revolution Project. And so here, what it is we find this case where oftentimes you have a professor that has a really good idea, and it doesn't really fit in a good box. So for example, maybe one of the specific programs at the DOE or companies aren't sort of ready for it. And so oftentimes what you need to be able to move the technology development along is just a little bit of a kickstart, fellowships, a little bit of support. Go manual here. And so what we've tried to do is pair faculty with really novel ideas with foundations and donors, so Doug being one of them, but Chisona's family being another one, to try and move an idea to the point where you can get it where you have a proof of concept, you can have a paper, a patent, something where you can take and you can really demonstrate you're onto something such that you can apply for a relatively large research program with the DOE or engage industry in sort of a fruitful collaboration and really build large, robust research programs. And so an example, so this isn't just some random picture off the web of some dapper-looking gentleman. It's actually Don Sadoway, who's a materials professor at MIT, and he does actually dress like that every day. He's kind of to the nines with his suits. So he had this really interesting idea, or there's this kind of challenge in large-scale storage where what a lot of people have been thinking about in terms of batteries is trying to get a device that you know that can store a charge and trying to teach it how to handle a high current, which is something you need for a grid scale application. And it's been really hard to sort of scale up something like a lithium-ion battery. And so he's kind of turned it on his head where he had this idea, well, let's take a high current device and try and see if we can't teach it how to store a charge. And so he comes from a metallurgical background, and so he's very familiar with aluminum smelters, which is like, there's no better example of a high current device. And so what he did was kind of turn an aluminum smelter into a battery by using a liquid anode, a liquid electrolyte, and a liquid cathode that are all density separated. And through just basically a fellowship supported by the Chisona's Foundation, was able to, you can't see this too well, but this is actually sort of maybe about 5 centimeters in the vertical, was able to sort of demonstrate this liquid metal battery concept at the crucible scale. And so you can actually see the electrodes and the electrolyte here. And this sort of proof of concept, just in terms of thinking about like the materials that were used and their abundance in the earth and how much they cost, the cycle performance that they were able to get kind of at this scale, so on and so forth, they think they're onto something, and they think they can do it at a much larger scale. And because they were able to kind of do some of these preliminary explorations through the help of the foundation, they're now able to, over the course of basically a year and a half, leverage that into an $11 million research program, both with Total for home-scale applications and ARPA-E, which is a new DOE program for much larger grid-scale applications. So we really think there's something to this model. If we can kind of help these projects along at just the earliest stages, that we can really get them ready to sort of really launch off with government and industry. So the program that I'm running the idea is to take this, first to continue to grow it within the solar and storage communities at MIT. That's where we have kind of some of our biggest areas of faculty interest, and there's so many ideas there that still need sort of taking off. But then also really to leverage it and to take this model and apply it to other renewables areas, and as well as enabling technologies, so things like grid, materials, so on and so forth. And so here's an example of a potential project which is perfect since Google has a sort of a keen interest in engineered geothermal systems. So Paul Waskow on the left, he does fusion power research. He works on a levitated dipole experiment at MIT. To do this work, you need a millimeter wavelength source at low power ratings to diagnose the plasma and get some characteristics about it, and at a high wavelength source to actually be able to inject energy into the plasma. And so what his idea is to take this millimeter wavelength source and use it for drilling. So I don't know if any of you guys have thought about laser drilling for engineered geothermal systems, being able to use it to drill hard rock. They think that it has a lot of advantages over laser drilling because the millimeter wavelength sources are much more efficient. You have much less scattering. And so they're kind of at the point now where they have the source and they just want to build a waveguide to be able to sort of try and volatilize some rocks. And if that works, then they think they can sort of take that to the DOE. So crazy idea, but also a really transformative one. And so this is the sort of thing where if we can just bring it to the point where sort of if something is there, we can sort of take it to the next level. So that's the program that I'm involved in, and I'll turn it over to Tonio now, and he's going to give kind of launch into some of his solar photovoltaics research and can kind of take a much deeper dive. So, Tonio.
Thank you, Daniel, and thank you, ladies and gentlemen, for coming today. It's an honor, but foremost a pleasure for me to be here today with you, especially given Google's commitment to renewable energies and sustainability. So today I'll be chatting a bit about our program at MIT focused on photovoltaics, and in particular the unique niche that MIT and universities can play in photovoltaics and the development thereof, focused on the scaling and cost challenges of PV. So I'll start with a basic slide that presents to you my motivation, my personal motivation on a month-to-month, year-to-year basis for working in PV. Obviously, on a day-to-day, week-to-week, I love being in the lab. I like working with students, and I like teaching and doing some fun research. So that's what keeps me going in the short term. But longer term, when I look in the mirror and figure, where am I going? What am I doing with my life? And what am I dedicating my time and energy to, which is really the biggest investment any of us can make. It's about solar, precisely because of the large resource base that's available. So on the left-hand side here, we have the resource, the solar resource that's provided by the sun, around 10 to the 5th terawatts. And on the right-hand side, that tiny little blue cube, it represents the human energy use, estimated in the mid to late century. And even if we consider the losses that occur in atmospheric absorption, what's reaching the Earth's surface is still several orders of magnitude larger than our energy use. Hence, if we can capture even a small % of that total, we'll be in pretty good shape. So if I look at solar energy today and ask, what is the status quo of the industry? We have a few pictures here of different solar energy installations. On the upper right, there's a winery in Napa Valley. On the lower right, there's a house in New York State. And on the lower left, we have a picture of a large field installation. The snaky white feature on the lower right part of that image is a road leading up to a large field installation of solar panels in the middle of the image, and the little green specks are trees. So you can get a sense of the scale there. It's an installation of several tens of megawatts. So solar today is a professional industry. It's on the order of $50 billion in terms of total movement. If you go to any of the large trade shows, you'll see it's a very professional environment, akin to any of the other large even software or hardware development in the IC and computer industries. It's competitive with bulk power in some markets, and I stress the point some in this case, due to the fact that still today the cost is high relative to conventional power sources. And as a consequence, total grid penetration, meaning the total amount of solar that's on the grid competing with fossil fuels, comprises less than 1% of total electricity generation, meaning there's a huge upside for this technology if we can get the cost down and allow it to scale. In terms of technologies, this chart here represents the total growth of the solar industry broken down by technology. So on the vertical axis, we have year, starting from 1980 and going up to a couple years back. And in the horizontal axis, the abscissa, we have the total capacity, the total annual production of PV. And since we're on an exponential growth curve here, this is growing quite fast and already out of date. But as we see the breakdown of the technologies, this is still roughly representative of what we have today. So back in 1985, there was about a third split between monocrystalline silicon, which is representative of the integrated circuit industry, these circular wafers grown by the Shklovsky growth method, achieving solar cell efficiencies in the range of 15 to 23%. We have about 50% of the market, or today, back in 1985, about a third of the market, comprised of a large-grained polycrystalline variety of silicon, known as multicrystalline silicon. And that usually achieves efficiencies on the order of 14 to 16.5% due to the higher defect density that inhibits solar cell performance. And we also have a small but growing percentage of thin films today that achieve efficiencies usually somewhere in the range of 6 to 10%. Now there's some newer technologies that might be even pushing 13. So if you look back to 1985, there was about a third split between these three groups of technologies. Today, the market is largely dominated by crystalline silicon because this particular technology was able to scale faster, and because of the higher efficiencies, there were less costs downstream. For instance, if you have a higher efficiency cell, you need less encapsulant materials, less labor to install the same amount of power, less racking materials, and so forth. So because of this efficiency lever, these particular types of technologies were cheaper and able to scale faster. And we have the situation where we're at today. A large percentage of the market dominated by crystalline silicon technologies, a small but growing percentage of thin film technologies. And in today's talk, we'll be talking a bit about both technologies, both the crystalline silicon and thin films, the incumbent and the emerging technologies. So I've told you a little bit about the status quo, where we're at today. But what I really want to talk to you about is the vision for PV, where I think we can go from here. And I think I'm fairly well convinced, based on the calculations that we've done and also looking at other technologies that have gone through similar growth curves, that a significant fraction of the world's energy portfolio can derive from PV within a few decades. And the advantage, obviously, is that it's a clean, renewable energy source, can be produced and manufactured and used locally. I emphasize here the word portfolio, energy portfolio. I'm not exactly a nut who thinks that all power will be coming from solar and we should turn off all of our other power plants immediately. No, I think that solar will play a role. It will play a part in the energy portfolio that will be comprised of other sources as well. But I hope for the future of our planet that these will be renewable and clean in the sense of non-CO2 emitting energy sources. I also envision a future in which solar panels are so cheap to manufacture that they can be produced locally. Say, for example, glass. Glass is manufactured locally typically and used locally because it's so heavy and cheap to manufacture. It would be impractical to manufacture overseas and ship around. So we can envision a future in which solar panels reach the same level if we can reduce the cost of manufacturing. There's another element to the vision here which relates to the map below, and you can see the solar distribution around the world and sunlight heavily concentrated in the so-called developing regions of the world. And on the next slide here, we have a cute little chart that I came up with some late night thinking about solar, where we have the Human Development Index, the HDI, which is a United Nations index of human development, versus insolation, the total amount of sunlight that a particular region on average receives on a daily basis. And you can see that those regions that are developing, that need energy the most, are also the regions that fortuitously have the highest amount of sunlight available to them. So I'm quite hopeful that PV can be a development enabler and a conflict reduction vector in the process of human evolution. So this is the grand vision for solar and for PV in particular, the conversion of sunlight into electricity. Now, regarding getting there, how do we actually move from where we are today to where we need to get? How do we make this vision a reality? Well, we're here. We're at a relatively small fraction of the world's total energy mix. And if we maintain a steady clip, a steady growth rate, we should be reaching some meaningful percentage of world electricity generation. And I emphasize electricity generation. It's not fossil fuels that are dedicated to the transportation sector here as well. This is solely electricity. I do think that within a few decades, if we keep it up, we can get there. But there are two obvious challenges to scaling. The first, which most people are familiar with, is the cost issue. We know that in most markets, PV is not cost competitive, that if you take power directly out of the wall, power being produced by a nearby natural gas-fired power plant, coal power plant, nuclear or hydroelectric, that PV will usually not be competitive in most markets, with certain exceptions. California, Tier 4 and 5, Hawaii, and so forth. But as the costs continue to come down, you'll hit grid parity in other markets, and the growth should accelerate. The other element that most people are not necessarily aware of is the sheer scale of manufacturing. Now, since manufacturing went overseas in the United States to East Asia and other locations around the world where the labor costs and materials costs are lower, we've somewhat forgotten this element, but it's very, very important that we keep it in mind when we think about producing terawatts of power. If we take the current manufacturing facilities for the dominant technologies out there in the market today, crystal and silicon, right here what you see is a CAD rendering of a 1 gigawatt fab for producing solar modules using crystal and silicon technology. This is REC. It's a company based in Norway. It's REC's plant that is located in Singapore. Now, if we take that factory and scale it up 1,000-fold to get to the terawatts level, what we really need to be aiming for if we're going to be producing meaningful percentages of the total world power, we're looking at land areas just for the factory alone on the order of the size of the state of Rhode Island. These are the left two bars in this figure right here for crystal and silicon and thin films actual. If we envision another reality where we have a much faster manufacturing process, for instance, the Pilkington float glass process, which is used to produce most of our glass, if we envision that instead producing solar cells, we would need much less land area because of the higher throughput of that process. And lastly, on the far right portion of this plot, we have the high-speed printer, the laser jet that's firing out 55 pages a minute. And if each of those were a 15% solar cell, we would need an area the equivalent of the size of 5 football fields, which at that point, everybody could do. Any country could have their own little football field dedicated to solar cell manufacturing, and off we go. So it's not only a materials challenge, but also a manufacturing challenge. And I want to highlight these 2 points as we move forward. Oh, one more thing. Even if we use a very, very thin layer of solar cell material, if we're going to be producing this on the terawatts level, we're producing tens of thousands of square kilometers of this material per year just to replace the modules that are going out of service. And that equates to a very large, massive material, something on the order of the Empire State Building per year in terms of materials processed to keep these very thin layers of solar cell materials active in the field. So that limits us in terms of what elements we can actually use on the periodic table. There are many that are too rare to serve for large-scale solar production. Okay, so we've talked a little bit about the motivation for solar, the solar status quo, the vision of what we can achieve in the future, some of the big challenges. And now I'd like to talk a little bit about what we're doing at MIT to address these challenges. And back in 2007, when I first landed there at MIT, to start as a junior professor, the vision was to to create a laboratory that was 100% dedicated to solar. And I think we've done a decent job at growing up. Now in September of 2009, we have a group of around 15 people and a nice balance of folks from around the world and different backgrounds and life experiences, but 100% dedicated to PV solar research R&D. And we are use-inspired, which means, well, this is a kind of funny term, use-inspired. Why do we, what does that mean? It's actually a code word for government funding agencies. You see, if you go to the certain agencies within the Department of Energy and say the word basic research, you get kicked out. They only want applied research. If you turn it on its head and go to the National Science Foundation and utter the word or the phrase applied research, again, they'll kick you out into the street and say, we only do basic research here. So use-inspired is a way for us to say, look, we need both. And we need basic research, because we need to understand some of the fundamentals and how to make breakthroughs in areas that haven't been made yet. But we also need the applied side. We need to understand how we take these fundamental breakthroughs and introduce them into real-life systems to make a difference. If it just stays in a thesis on a shelf, it's not going to do much good for the planet, and it's not really going to justify our existence. So we start from a cost model in general, if we're looking at a cost reduction. And efficiency here is a huge lever on your cost. There are also other things that are completely outside of our control, like the interest rate on the loan you get to build your solar facility. That has about the same influence as efficiency. So there's both business and technology-related challenges here. And we also emphasize medium-term real-world impact. Now, it would be so much easier for myself as a professor just to say, oh, I'm going to be working on some really far-out project, and in 40 years when I retire, the world can judge me. Instead, I put my reputation on the line on a regular basis and say, okay, within 5 years, we hope to have this accomplished. Within 2 years, we hope to have this accomplished. The reason I do that is because there is an urgency to this problem of climate change, and we have to get moving quickly. There's another element to this as well. We want to help the students who will be graduating in 2 to 5 years. If we set them loose on a project that's of fundamental importance today, and that will be bearing fruit within 2 to 5 years, then when they go out into industry, they're sought after commodity, and they're much more likely to get a position. So let me highlight for you a few of the examples of the instances in my own career that have led me along this path of medium-term impact. As a graduate student in Berkeley, we developed some technologies that spun off into a company called Cali Solar, which is located just up the street here, using dirtier forms of feedstock material to make high-efficiency solar cells. And we also have developed some newer technologies more recently. This is a map of current collection efficiency that are improving battery regions of solar cell materials that are now implemented in commercial production. So it's kind of fun to visit Cali Solar's factory early today and see some of the technologies under development being actually used out there in industry. So it was thanks to these advances that we're, I think, one of the rarer research groups that's actually carbon positive right now. Our efficiency increases in industry have offset the insane amount of traveling I do running around giving presentations and the like. So I'm motivated to keep it that way, and hopefully we'll continue making advances that continue to improve solar. So let me give you a few case studies. We'll get into the science, and I would like to make this as interesting as possible for you. So if I happen to breeze over some of the subjects and you really want to talk about them, we can go back to some of the details in the Q&A. Number one, we're going to talk about multicrystalline silicon. Again, the technology that comprises about 50% of the world's market today. And the reason we're focusing on this is because many of the established companies are very risk adverse. This is a commodity industry where you're producing a product that will last for 20 years. It's like the building construction industry. So there's a very high risk. If you do something new and it doesn't work out and you have a massive module recall, it's going to cost the company quite a bit. So at the same time, breakthroughs are sorely needed. There is a strong driving force for innovation to drive the cost down and improve the scalability of these technologies. And it's motivating for the students, I think, to have this shorter time to market impact in this particular field. So let me give you an example here of multicrystalline silicon. This on the right-hand side is an image of a silicon nitride coated multicrystalline silicon wafer on the order of about 5 by 5 inches. So you can get a sense of the beautiful crystal pattern. This is a picture of the crystal growth area within the production facility for these multicrystalline silicon materials. And you can see here on the lower right portion of that image a small keyboard and monitor for size comparison. These are rather large furnaces. Each furnace produces ingots, between 1 and 4 ingots, somewhere in the range of 250 to 400 kilograms. Today they're even going up to 600 kilograms, and 1-ton ingots are in R&D stage. So these are massive blocks of silicon. And out of those blocks, you can see the size here of the crucibles with one of our students, Sarah Bernardis, as a comparison. The number after the gen refers to the number of wafers along the linear dimension. So Gen 5 would be 5 wafers along the linear dimension, 25 wafers total along each thin delta Z of your crucible. And out of these crucibles come material that looks something like this. These are columnar growth structures starting from the bottom all the way to the top. And then you slice your wafers out horizontally, and your grain boundaries are running perpendicular to their surfaces and don't interfere much with charge transport. So we have this sort of material. How can we do better? Where are we at today, and where are the opportunities for innovation? Well, if we were to look inside of the material with a little bit of X-ray vision here and to detect the defect clusters within the material, we would see these defective zones going from the bottom of the ingot all the way through the top. And these are zones that contain dislocations, which are essentially one-dimensional line defects within your material, on order of 10 to the 4 to 10 to the 8 dislocations per square centimeter. Anybody who's worked with integrated circuits or lead-emitting diodes, for instance, knows these are very, very high values, very detrimental for electronic properties of a semiconductor material. Now, to illustrate that in a more sciencey form, we have performance in the y-axis and dislocation density in the x-axis here. As you increase your dislocation density, your performance comes down. We have some magic number here where we have better solar cells with lower dislocation densities and worse solar cells above. If you get down to this number, 10 to the 4 per square centimeter, this magic number, then solar cell performance is not really influenced much because the probability that some electron inside the material will encounter a defect is very, very low. Now, let's take a wafer out of a vertical slice, shown here by this little box. And if we scan that region using an electrical performance mapper, we realize that there are some really bad regions caused by regions of high dislocation density. Likewise, if we take a wafer in the cross-section, as we're apt to do when we actually produce a solar cell, we find that the wafer itself has a checkboard-like pattern of these bad regions together with the good ones. And what that means from a practical point of view is that if you have the good regions and bad regions all connected together through a parallel circuit through the front surface emitter and the back surface metallization, the bad regions will drain current from the good ones, and the overall performance of your device will be reduced. So these dislocations are public enemy number one in terms of solar cell performance. And a lot of work has gone into it in the past to try to figure out how to reduce their impact on solar cell performance, usually after the material is already made and while you're doing the cell processing steps, the phosphorus diffusion, the anti-reflection coating deposition, trying all sorts of things. Well, as a starting professor at MIT, had a completely blank slate, we said, well, why don't we try something very, very different here? We know that dislocations are manipulated in metallurgy, in the steel and aluminum industries. So why don't we go ahead and try to apply some of that learning to multicrystalline silicon solar cell material? We know that at low temperatures, dislocations really don't move anywhere. Silicon is a brittle material like glass. If you push it, it'll deform elastically, meaning just bonds will stretch but won't slip. And eventually, if you keep pushing, the thing will just shatter. And the same is true for silicon. So at room temperature. As you start increasing the temperature a bit, you can actually have the material deform, just like a paperclip would, a piece of metal, a ductile material. You've gone above the brittle to ductile transition temperature. This for silicon occurs around 500 degrees Celsius, but because of the unique crystal structure, you're still limited to how mobile these dislocations are. You really need to go above 1,000 degrees C before you start getting dislocations moving freely throughout the lattice. And note that silicon melts at around 1,400 degrees Celsius. So these are very high temperatures. And this little dislocation core structure, denoted here with this defect, is free to move around the lattice. So with this knowledge in our minds, we sought out some ceramic annealing furnaces and developed a process at MIT where we can eliminate the dislocations inside of these multicrystalline silicon materials. So on the bottom part of this figure, we have a control wafer with these little pits that correspond to dislocations after the sample has been defect etched. And on the top, we have the annealed sample, which is essentially taken from an adjacent part of material where we demonstrate that the dislocations have been effectively removed. And we believe that this process, if done correctly, could be done for about a cent per wafer, a penny per wafer, which is really, really promising. If we can implement this and manage to scale it up, we have a few more tests to run in the laboratory. I'm really telling you some of the cutting-edge research that we're doing in our lab. But if we're successful in ramping it up, we could, for a mere penny per wafer, be increasing the efficiencies of these solar cell devices anywhere between 10 and 40% relative to where they are today, which is a big deal. And we're pretty excited about it. So let me zoom through these slides since we'll be discussing more about that in the Q&A. But the takeaways from this first part here is that there's plenty of room for innovation in existing commercial PV technologies. And anybody out there who says, well, you know, it makes no sense to dedicate any time to commercial technologies because there are big industries thinking about it, I would say, actually, the big industries are looking in the areas where they think they can have the biggest impact and the lowest risk opportunities. If you come along with a great idea that the industry thinks, that's too risky, maybe somebody tried it back in the 1970s, it didn't work, don't waste your time, I would encourage you to go ahead because maybe, just maybe, you'll strike upon something really interesting. You really have to take advantage of the years of insights gained in parallel fields, especially those fields that are going out of vogue, like metallurgy. It's not often that you hear a new department from a new university forming the metallurgy department. No, actually, if you speed back 50 years, when steel was the big material that everybody was researching, you'll find that many of the material science and engineering departments were called Department of Mining and Metallurgy, or something equivalent thereof. Nowadays, it's the Department of Nanotechnology, which is great. We should definitely be looking into new materials, but we also shouldn't forget the wealth of knowledge that there are in these fields that are now going out of vogue. Just because the light is shining in that corner of the room when you've lost your keys doesn't mean that your keys are over there. They might be somewhere else in the room, and you might have to create your own light to go looking for them. The third part is that I just wanted to mention this point, that the model for funding research within universities is changing a bit. As Daniel alluded to before, the involvement of individuals within university research, philanthropic individuals, is very important. And it was actually Doug and Barbara Sprang that allowed this project to get off the ground when it was still an idea in our minds. Me as a starting professor without many resources to get started with, they were the ones who actually oiled the machine and allowed things to get started and some first proofs of principle. Eventually now it's funded by a DOE project. So that's an interesting part. So we're going to change gears. And move from the existing crystal and silicon technologies into some of the thin film technologies. If I might remind you of that previous slide at the beginning of the talk, thin film technologies today comprise a very small percentage of the total solar produced. And however, there's a large potential for thin film technologies for the following reasons. There's a scalability argument to be made. These thin film materials use 100 times less materials than standard crystal and silicon technology. To give you some concrete numbers, the absorber layers, the active layer materials, are typically on the order of 300 nanometers to 3 microns, as opposed to a standard silicon wafer, which is on the order of 150 to 180 microns thick, which is about 4 times the width of your human hair. So you can imagine how thin these thin film layers really are. But because they are so-called direct bandgap semiconductors, or take advantage of very good light trapping, they're able to get away with much less material. There's also the potential for very high throughput manufacturing. With a thin film technology, one could, in principle, produce solar cells as shown here on the right. This is a picture from Unisolar, an engineer here processing solar cell materials onto a roll of stainless steel foil. And that's, of course, a big step forward in terms of manufacturability, where we're producing solar cell materials like newspapers. The challenges, however, are twofold. To date, thin film materials haven't been able to achieve very high efficiencies and thus haven't been competitive in the bulk market when you have more efficient solar panels that require less labor and less materials to install per unit power produced. And secondly, the conventional thin film materials will ultimately be limited in how fast they, or how much they can scale because of the materials availability. Now, we'll get to that in a few slides. I'll come back to that point. So the research goal within our laboratory is to design scalable, earth-abundant thin film materials, meaning materials that have a large enough natural abundance in the earth to scale to the terawatts level. So the functional requirements, if we think about this from a design engineering perspective, we have to have an efficiency of about 15% or more. It has to be able to absorb sunlight very efficiently, generate a high volume of charged carriers, and minimize the carrier collection loss within the material. And so there are some design parameters that relate to the material properties that we have to design for. And the constraints are essentially the ability to scale up to the terawatts level and low cost, and of course, durability. So let's focus on this scaling up to the 10 terawatts level. I'll show you some numbers. If we look at the periodic table and we assess which elements out there are abundant enough to be deployed in the tens of terawatts scale, we're looking at about 50 of them. And out of those elements, there's a subset of the elements that are produced in a high enough volume of manufacturing today. There's about 30. So these are materials today that are manufactured at scale. And if we take those 30 elements and begin combining them to form semiconductor compounds, we have a number of possibilities to choose from. And by screening, both experimentally and theoretically, using some very sophisticated computer modeling by a colleague of mine, Gerd Sater, in the Material Science and Engineering Department, we're able to hone in on around 10 compounds that really show some good promise for making thin film, earth-abundant solar cell materials. However, if we start comparing the real efficiencies, the record efficiencies of these materials versus the theoretical maximum, shown here, this plot is the theoretical maximum efficiency as a function of band gap. And we compare the actual record solar cell efficiencies for several compounds, including iron sulfide, tin sulfide, copper zinc tin sulfide, cuprous oxide, and tungsten sulfide. We see that the record efficiencies of these earth-abundant compounds are much, much, much lower than the theoretical maximum efficiency. And this is after several years of work, especially during the 1980s, on these particular compounds. Compare that to crystalline silicon. The blue are the record cell and module efficiencies. The red are the typical commercial cell and module efficiencies, head and shoulders above the earth-abundant compounds. So the question is, since these materials underperform, are they intrinsically limited by some fundamental electronic property of the material? Or are they limited by defects, the same way that crystalline silicon is limited? And of course, when the word defect comes along, my ears perk up. I'm, of course, fascinated by these defects. They're not only bad, but in many cases quite good. You can think of examples in the real world around you where defects are actually helpful. For example, anything from strengthening steel or aluminum. You add impurities to strengthen. Steel in particular, stainless steel, you add chromium to form a passivating layer of chromium oxide that prevents oxygen from going in and corroding the steel. Now you can even have examples of colored glass or gemstones that gain their color by the presence of certain point defect impurities. So defects here are very valuable in certain cases, but of course detrimental in others. And for solar cell materials, as we just saw in this example, we have some detrimental effects. So our first step is grain boundary engineering. We want to make sure that these materials have large enough grains such that the grain boundaries do not inhibit carrier transport. And let me just show you here the grain boundaries highlighted in a cross-sectional scanning electron microscope image of a thin film material. If this is our little electron at the bottom, it has to be able to make its way out of the material without interacting with the grain boundaries. So the grain size has to be on the order of 5 times the thickness of your material. If you have about a 1 micron thick solar cell material, you need grains on the order of about 5 microns thick. And this is just a quick little simulation to show you that point. So we've been doing a lot of work on trying to increase the grain sizes of these thin film materials. For example, this one, a cuprous oxide earth-abundant solar cell material. We have a layer somewhere in the order of 100 nanometers thick, and we're trying to achieve grain sizes in the order of 500 nanometers or more. You can see that we've managed to increase it quite a bit. And just last week, the student on this project showed me a figure that I wasn't able to incorporate into this, which basically had grains that were larger than the little box that I'm showing right here. So really, really large grain material. And the resistivities of these materials were such that they could be incorporated into devices. That's our next step that we're working on. And hopefully with any luck, knock on wood, we'll be able to beat the efficiency limit and have a record efficiency cell if we can get above 2% efficiency. It's not a high bar to cross. So we're working on this avidly at MIT, and hopefully we'll make some nice progress over the next year or so on this topic. So takeaways in this particular subset. We have novel earth-abundant thin film materials, which we believe offer great potential for substituting out the commercial thin film technologies on the order of 5 to 10 years. And now this basically says, guys, don't go out and sell all your stock in First Solar or give up on all the SIG startups in the Bay Area. No. There's still several years that cadmium telluride and copper-indium gallium diselenide can continue producing before you start running up against resource walls. But many people think by about 2020, we'll start hitting these walls of material availability, and we'll need new technologies to overcome that. That's really the niche that we're attempting to develop right now. The second take message is that current earth-abundant solar cell materials are underperforming. We believe that it's in part due to defects. We see some evidence for this already. And by defect engineering, the same types or general classes of techniques we've developed for crystalline silicon applied to thin films, we believe we can overcome these efficiency limits. So the next few years we'll be able to tell whether we're successful or not. And in conclusion, so we can open it up for Q&A. The potential of the solar resource is very vast. Terawatt scaling is possible if certain challenges due to scale and cost can be overcome. And most importantly, at this very early stage of the solar market development, a very small innovation can go a long, long way. If you make an innovation today and the market continues to grow up, you can envision a situation in which your small innovation impact over tens of percents of total market share if you develop a very successful product. So with that, I'd like to really conclude by acknowledging the team. It's not myself doing this work. It's an entire team of people comprised of students, undergraduate and graduate, postdoctoral fellows, and research scientists. And we have here the team up here and our collaborators internationally and nationally, and our funding agencies, of course. And with that, I'd like to open it up for Q&A and perhaps turn it back to our MC or open it up for, yep, we'll just open it up straight for Q&A, make it efficient that way. So, question in the back. Yeah. So the question was, are most earth-abundant materials sulfides? Yes, there are several earth-abundant materials that are sulfides. These have some very interesting material properties. They're very typically covalently bonded materials or near covalently bonded materials that allow for nice charge transport throughout the layers. You don't have as much charge localization as you might have in oxide. So yes, they are quite popular.
I get this gentleman. Excuse me, sir, on GVR, remote GVR, can you hear us?
Sir. Yes, sir.
Nope.
Would you like to stop the recording?
No, don't stop the recording. We just have somebody typing on the keyboard, and it's making a little bit of
I'll mute them.
audio.
Got it?
I think they, yep, okay, fantastic. Yes, so.
Yeah, that's not the right
So-
one.
Yeah, so the question is, can sulfides react with the environment? Most certainly. So this is one of the disadvantages of sulfide materials. They are rather reactive, and as a result, the encapsulation becomes very, very important. There's one type of sulfide material in near commercial production today. They're just at the cusp of commercial production. It's called CIGS. It means copper indium gallium disulfide. And this particular type of material needs to be very well encapsulated to avoid any sort of degradation due to exposure to the elements or ingress of gases and moisture through the encapsulants to the active layer materials themselves. Because they're very, very thin layers, they're extremely sensitive to the ingress problems. Yeah. Question in the front, yes.
I can't remember the name of the elements, but I read about a couple of elements that if you adjust the ratios of them, it tunes the band gap. And you could make multi-layer crystals that were very efficient. Do you have any comments about research on that? Or?
Certainly. So the essence of tuning the band gap, so the band gap basically means the energy at which the semiconductor begins to absorb light. And anything with a higher energy than that, the semiconductor can absorb light and transform that into electrical current. So the band gap is a very important material parameter. You match that up with the solar spectrum and try to absorb as large of a solar spectrum as you can. And the material will absorb light most efficiently at the band gap energy. So you can stack different materials one on top of one another that absorb most efficiently at different regions of the solar spectrum, thus achieving a very high efficiency solar cell. So to make a long story short, yes, you can tune the band gap of materials by alloying them, by, say, for example, taking 3 elements and changing the ratio of the first and second element so that you go from a low band gap material to a high band gap material and absorb very efficiently the reds and the blues of your solar spectrum. While certainly there's efforts in these directions, one usually does that once one already has an established solar cell material. So the first step is to get a solar cell material that works with some band gap. And then from there you can innovate and alloy and change the band gap properties. So we're one step behind that still in terms of the earth-abundant compounds. In terms of the non-earth-abundant compounds, they're already quite there. With the 3,5 compounds, certainly indium nitride, indium gallium nitride, and other compounds, you can alloy in this way. Yeah.
So up there is one of the goals. You had $1 a watt at the module level. It used to be $1 a watt installed. The bar seems to be slipping. First solar is already there, but they're not economic. I mean, we can improve efficiencies, but even if you double it, it's not grid parity in most areas of the
Sure. So the question was, the dollar a watt on the module level, the premise here was that First Solar produces solar cell modules that are $1 a watt on the module level, but because of the high installation costs, these are low efficiency panels, because of the high installation costs required, you wind up with an installed system cost much higher than $1 per watt, and it's still not cost effective. So as one of the requirements that I had earlier in the slides, a baseline efficiency of 15% was what we're targeting. And with those sorts of efficiencies, if you have $1 per watt, the installed costs become lower as a total percent. So there is an element there embedded. Perhaps I didn't express it clearly enough. A more precise way of saying that would be exactly as you recommend, the price at the installed system level, which does capture the efficiency trickle-down effect. Personally, I think that a large fraction of the cost that can be squeezed out of solar cell production is not only on the materials and the manufacturing side of things, but also on the balance of system, on the module level, and on the installation side. And we were touring some companies this morning that are doing innovations in this area, here in the Bay Area, in the installation and better framing materials and better ways of installing them. Certainly, there is a lot of leverage to be gained there. If you look to Germany, the price of installation is about half of what it is in the United States, in large part due to more streamlined processes for installation, including the bureaucracy involved. So there are a number of different pieces that can be you can squeeze cost out of, and ultimately those efficiencies will need to come to bear if we are to produce solar at the terawatt scale. So yes, would be my answer. Yeah.
Are there any innovations along the lines of proposing materials related to CPV? It seems temperature is a big problem.
So what are the materials innovations in concentrating solar power? That was in CPV. So CPV is a technology in which you utilize optics to concentrate sunlight into a very, very small cell. And you can spend more money to produce that cell because you're taking light from a larger area and concentrating it down. So in terms of total cost of production, the balance of system components, the optics and the structure around it ends up being comparable, if not much greater than the actual cost of the cell itself. So it's fascinating that type of technology, because you can envision a scenario in which maybe a better cell comes along in 3 to 5 years and you just swap it out and you haven't changed the total price of your system much. A lot of innovation goes around managing the heat load in these devices. And because you're concentrating 500 suns, up to 500 suns, it can be less, but up to hundreds of suns onto a very, very small area. When I say a sun, that's the equivalent of going out and standing in midday sun. You can imagine 500 times that amount of heat. That's a lot of power to dissipate. Any inefficiency in the solar cell device will usually generate heat, and you have to extract it somehow. So there's been a lot of work going into the materials used for the packaging and heat extraction from such devices, and as well into the materials that comprise the active layer solar cell itself. So in those cases, goodness, if you concentrate enough, it becomes impractical at very high concentrations due to the heat load. But if you concentrate enough, it might reduce some of your material constraints as well. You might be able to, instead of 30 elements, you might have about 34 or 35 to deal with on the periodic table, which could open up some possibilities as well. Yeah, another question.
You had a slide that talked about 2020 or 2030 sort of being on the trajectory for 25%. Yeah. Then you had another slide where you were talking about what that meant in terms of the factory size being more careful. What about the area for the solar cells themselves? Yeah. For that level, where do you anticipate these things being placed? Is it only on roofs? Is it on dedicated facilities like that one slide that showed us the entire hillside?
Yeah.
Any thoughts on that?
Certainly. So today, some of the most cost-effective installations are large field installations, largely because you don't have to worry about some of the safety regulations of installing it on the rooftop of somebody's house. You can just put up a big fence around the area, install a bunch of modules all at once, and then only pay for one architect and one design engineer's fees for a very, very large field installation, and negotiate down the price per module with the supplier because you're buying it bulk. So these field installations are price competitive today, but I really do hope and secondly expect that the residential market will comprise ultimately a large portion of the demand, because we pay a higher price for our electricity than commercial suppliers do. And secondly, if we produce the energy locally, we're using it locally as well, and we don't have to pay for the transmission and distribution of that electricity. It's not a commonly known fact, but if you're buying coal power, the total price that you pay, or the total cost to get it to your home, half of that is a transmission and distribution cost. The other half is the production. So if you produce your power locally, you're producing it on your roof and consuming it locally. I think that's ultimately where the market has to head. Now the question is there enough roof space in the United States to actually make that happen? Barely. And I would add furthermore that we shouldn't bank on it. I think rooftops definitely should all be covered, or at least the practical ones should be covered with good solar panels. But there are also other opportunities of dead spaces around the United States that we can consider covering. Let's take for a second the total road coverage in the United States. If you look at the total network of highways and roads around the US, you can download these numbers from the government, and you look at an average width of a road, you multiply the two together to get the total land area, you're looking at a fraction between 1% and 2% of all the United States covered in asphalt. It is an amazingly large number. You look at other types of things like the percentage of Virginia covered in tobacco farms. It's also in the order of percent. So there are examples of human-made structures, perhaps not the tobacco farms, but roads and parking lots that could be considered as well for installation of solar panels. And the parking lots being a great example if you install them on covered lots. So I think we have enough dead spaces already, spaces that aren't being utilized, that we don't have to take new pristine land and produce solar panels there. That might be a good way to get the industry jump-started near term, but longer term, there are certainly a lot of options for us with the spaces we've already created. Yeah, question?
So your notion of looking at these abundant earth compounds is not, so new. I think in fact, a couple of years ago, it was you at Berkeley who was talking about this. Where else is it going on in the world, and should we be collaborating with them?
Absolutely. So the earth abundant materials, the question was, it's not such a new idea. There have been people investigating this for several years. Absolutely true. So the history of earth abundant solar cell materials, I believe, started way back in the 1970s or perhaps early 1980s. CIGS, copper ammonium gallium diselenide, actually started from investigations of copper sulfide and the realization that this material wasn't stable. The copper tended to electromigrate, so let's add some heavier elements in there to stabilize this and get a firmer structure. And then from there, they added indium. But at any rate, the research that's been going on, let's see, some of the big names in the field, Freundlich in Texas has been investigating this, Alex, for quite a bit. Other groups, Cyrus Wadia from Berkeley produced a great paper where he looked at the economic aspects together with Dan Kamen. And there's been a growing enthusiasm for this idea in the field. Now, the ultimate Achilles heel for all of this is that we haven't been able to really make one of these earth-abundant materials work on a large scale, precisely because of the efficiency issue. There are different types of problems that affect each type of material, and we're just now beginning to get a sense and an appreciation of the limiting factors for each of these. Let's take sulfides, for instance. A lot of work went into sulfide research here in California several decades ago, and the Hahn-Meitner Institute, which is now the Helmholtz-Zentrum Berlin, in Berlin, Germany, during the 1990s, working on compounds like copper sulfide and iron sulfide. And we just didn't get critical mass, is my belief. And I do think that the key efficiency limiting defects for each of these different materials are on the cusp of being identified. And if we can identify them and if we can overcome them, then these materials have a chance. But if we just go by brute force alone, trying to deposit them and make solar cells out of them, we won't get anywhere. Good. Well, I'll turn it back to our MC. I do thank you for your questions. It's been fun being here, and thank you.
Thank you, Tonio. And thank you, Daniel, as well. Okay, so just about done. Just to let you know that we do have some handout material over here, which give you a lot more information on some of the other programs that are involved in MITEI and the Sustainable Energy Revolution program, and some actual interesting background articles about some projects that are possible in the area of wind, geothermal, and storage. So you're welcome to have those. Also, if you'd like to sign up to receive the MIT Energy Initiative newsletter on a regular basis to see what's going on at MIT, some of you have already signed up over here, but others that haven't yet, please feel free to do it. And in the bold hope that any of you out there may be actually interested in funding some of this research, just come and talk to either Richard over there or me after this is over, and well, we'll be happy to follow up with you. So that's it. Thanks very much for coming, and thank you out there, viewing audience. I hope you all enjoy seeing it on YouTube. Thank you very much. Bye-bye.